Hello, and I just wanted to give you all a few good pointers on how to use these notes in a Truss problem analysis. And so it may be a statics problem or something like that that you're working out. Could be an engineering course that you have, maybe even a high school course. I'm going to go through what I think are some better simplified steps on how to solve the method of joints. And so there is other versions that you could use where you're actually looking at it from the member's perspective, but this is actually from the joints perspective. So I have four broad steps here that we'll dive into in just a minute. First of all, we have a free body diagram that we're going to draw out. We're going to look at all the forces on the joints. We're going to look to see if it's statically determined, which would follow our equation of 2J equals M plus R. We're going to find all of our external forces by utilizing the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, and the sum of the moments equals 0. If you're in a physics background, you might say that it's the sum of the torques equals 0. And so there's just kind of a difference in the terminology between the different groups of people. The fourth step is where we'll actually spend quite a bit of our time. We're going to be looking at finding all of the internal forces. And so it says here that we're going to find our internal forces by using the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. But we're going to loop through that several times until we find all of our internal forces. So that's kind of the big picture here. You'll notice also that in step 3 here, we're utilizing the sum of the moments equals 0. We don't use that in step 4. We'll be able to figure things out just from the forces components in step 4. Okay, so on step 1, we're going to always draw reaction forces up and to the right. I'm going to choose to do that. So it's not necessary to do that, but in my consistent way of doing it, that's the way I'm going to do it. If we find the value of a force to be negative, then we will redraw that force in our free body diagram. The reaction at the pin is both horizontal and vertical. So we're going to say at the pin it's going to be right and up. And the reaction at the roller is only orthogonal to the roller. In our example here, it's actually going to be to the right. We're going to check to see if it's statically determinate. We're going to look at our moments equals 0, usually at the pin, because that allows us to eliminate two unknowns out of our equation. It makes it easier to solve. Reminder that if we're going in a counterclockwise direction, it's a positive rotation. If we're going in a clockwise direction, that would be considered a negative rotation. We're also going to look at our sum of forces in the x and y and redraw our free body diagram if any of the reaction forces are negative. Our method of joints, and so this is actually going to be how we go through and find what we need on this. We're going to choose a joint, and many times there are good choices and then there are bad choices. And so as you do more of these, you'll be better at selecting them. We're going to look at all the forces at the joint, and we're going to draw all members as they are away from the joint. When we choose to do that, we're looking at the force on the member by the joint, and the member force is opposite of this. So when we draw it out, it'll look confusing, and I'll explain why it's going the direction it's supposed to go. With that assumption, that assumes that the member is going to be in tension, and you'll see an example of that as well. Using components of forces, we're going to solve our Newton's laws there. We're going to update the direction of the force if it's negative, which means it's actually in compression. So if we come up with a negative force value, we're going to not only switch the direction of our arrows, but we will also recognize it as being in compression instead of tension. Here's a picture that will hopefully help us understand what's going on. So red is pulling to the right, blue is pulling off to the left. If a member, so the member, it would be the rod that would be between them. If a member is in tension, we think of it as occurring exactly as we have drawn here. So if we look at this, then the question is, well, what is the red doing on the member? Well, red is pulling to the right. Well, that's not the actual question that we want to ask. We don't want to ask what is the force by the person. We want to ask what's the force acting on the person. And so Newton's third law here comes into play, the equal and opposite or action-reaction pairs. And so simply because we have a red force to the right, immediately there is a counteracting force off to the left at this point. And so the joints are these people that are pulling. The member or the rod is between them. And so whenever we think about this being in tension, yes, red is pulling to the right, but the member is actually pulling back on red. That's actually what's happening to red. And so it's called the method of joints because we're going to be looking at all the forces that are acting on the joint. So this will keep coming up over and over again. You might start to get your head wrapped around it, and then all of a sudden it gets confusing again. Just realize that it's going to look exactly backwards from what you think it's supposed to be, but it's because of Newton's third law and what we're actually looking at. A couple things to just refresh ourselves of: sines opposite over hypotenuse, cosines adjacent over hypotenuse. And for this problem that we'll be working out today, I'm going to remind us that sine of 45 degrees and cosine of 45 degrees is about 0.707. And that'll be the trig value that we kind of keep coming up with over and over today. So here is our problem. We have a truss setup. All of our horizontal and vertical dimensions are 2 feet. We have a pin in the top right corner. We have a roller in the bottom right corner. And then we have these additional loads of 200 pounds, both at C and D. So our first thing that we're supposed to do is draw our reaction forces. So we're going to draw at the pin, both to the right and up. And at B, we're going to draw it to the right. Okay, this is my choice. I'm going to choose to always draw them up and to the right as needed. Pin gets 2, roller gets 1. The roller is perpendicular to its roller system. So as we go through this, we're going to look at our moment about the pin. So we're going to look at the sum of the moments at point A, and we're going to set those equal to B0. So whenever we look at this, we have a force here at B, a force at C, and a force at A. Now we also have force at D. We also have 2 forces at A that are not going to come into play because our moment equation is force times perpendicular distance. And so the distance between this force at A and A itself is 0. So the moment at A from the force at A is going to be 0. So I don't need to worry about either of these 2 forces. I am going to consider each of these other 3 forces here as we look at it. So the force at B is acting 2 feet away. So we're going to use this force times the perpendicular distance to the pin, or our rotation point, our axis point here. And so B is going to try to push not to the right, but as B pushes this direction, it would naturally tend to make it rotate around A in a counterclockwise direction. And so that counterclockwise direction will be positive. And our force then at B is going to be sub x, and the distance is 2 away, so positive 2bx. For C, it is 2 feet away, also from the pin in a perpendicular direction. So I'm not measuring this diagonal length. I'm looking at the force acting in this direction, and I'm noticing that the force in this direction is actually 2 feet away from A. It's technically this 2 feet measurement that we have here. And so again, it's not an up or down question here for moments. It's a question of whether or not, if we kind of anchored it here and let it rotate around A, C pulling down is going to make this thing rotate in a counterclockwise direction. So again, that'll be a positive direction that we have here. And then our force at D, our exterior load force at D, is 200 pounds, and it is 4 feet away. And similarly, it would be in a positive counterclockwise direction as well. Whenever we solve all of this, we get that B sub x, or the reaction force at B, is negative 600. All my units are going to be in pounds. I'm just going to leave those off for the rest of the problem. So since this is a negative force, that just simply means it should actually point in the other direction. So I need to redraw that going in the other direction, so I actually have it drawn off toward the left here now. So that was our moment. Now I'm looking at the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. we drop our clockwise, counterclockwise concept here. So we're not looking at rotational sense being positive or negative. Now we're actually looking at left being negative, right being positive, up being positive, down being negative. So our first one that we're going to look at is the sum of the forces in the x direction need to add up to be 0. So I have this b sub x here, and I have this a sub x here. Those are my only two forces in the x direction. I'm going to choose to always look at the magnitude of the force. So b sub x is going to be 600 that we found earlier, and the direction that's associated with it, I'll put as a plus or minus symbol in my equation. So b sub x is acting toward the left, so I'm going to put a negative in front of it, and the value of b sub x is positive 600. So all of my force values are going to be positive. I'll use pluses and minuses in my equation. When we solve this then, and we put b sub x as 600 in here, we find that a sub x is 600. It's positive, so I don't need to flip it around or anything like that. It's already pointing in the correct direction. So now I know these two exterior forces, reaction forces that we have. Now I need to find this one more. And by using the sum of the forces in the y direction, we'll be able to find that as well. So in the y direction, I have up, and then these two down. So I need to be consistent with my pluses and minuses. So 200 down, positive ay up. And I solve this, and I get ay equals 400. So I now know the three black forces that we have here, these reaction forces. I will point out that I did not do the 2j equals m plus r earlier to see if it was statically determinate. So our number of joints that we have here is 5. So 2 times 5 is 10. The reaction forces, there are 3. There are these black forces, reaction forces here. And the number of members that we have here are 7. So we actually end up with 2 times 5 equals 7 plus 3. So this problem is solvable for us. Statically determinate doesn't mean that it can or can't be built. It just means that with our techniques that we would be able to solve it. So our situation then now actually started out with this picture. We updated B to point off to the left. And so this is the picture that we have here, drawing a free body diagram at every single joint that we have. And again, I'm going to draw in the direction, you'll notice that I've included these blue arrows here, in the direction that the members are going. So at A, I have 5 forces that I'm going to have to deal with. The force from the member AC, the force from the member AE, the force from the member AB, as well as the 2 reaction forces that we already found here. Again, in the direction that I have it drawn, as I had mentioned earlier, this is actually going to cause each of these to be in tension. So a force vector drawn this direction is going to actually make AC be in tension. Again, that's backwards from what we normally think because we're not looking at the forces on the member, we're looking at the forces on the joint. Okay, so we're going to pick one of these joints and look at the sum of the forces in the X and Y direction to try to find out the forces in the members. I'll point out that we will be done when we find all of the reaction forces, we've already found 3, as well as all of the internal member forces. And so I'm looking for 7 internal member forces. When I finish all of those, we'll be finished with. So I've gone ahead and labeled our forces that we're going to use here, AB, AE, AC, and so forth. And so we're going to choose one of our points to look at. I'm going to start off with B. So at B, I have 1 force in the Y direction and 2 forces in the X direction. So we're going to just go ahead and pick our Y direction force here. The sum of the forces in the Y direction have to add up to be 0. Well, right here, AB is pointing up, and I'm going to set AB, that force. AB is a single force, not 2 forces multiplied. It gets set equal to 0, and so I actually know the value of AB now. AB is actually equal to 0. In the X direction, I have 2 forces. The BX is pointing to the left. I'll signify that with the negative sign. BC is pointing to the left. I'll signify that with the negative sign in front. I already know the value of B sub X to be 600. We'll plug that in, and we will get an answer of BC equaling negative 600. Okay, one of the things we said is when we're looking at our member forces, if we come up with a negative value, that means our arrows are drawn the wrong way. So we're going to have to switch the direction that they're drawn and recognize that this is actually in compression. So I'm going to show compression values in green throughout. So whenever we do that, I've redrawn the arrow for BC, but notice that I've redrawn it on both sides. So I've redrawn it to the left over here at C and to the right over here at B. And then the BC value is 600, but it's actually in compression here rather than in tension. So that rod is being squeezed, but we draw them away at the joints. Okay, at A, that just happens to be the next one I'm going to pick. By the way, we could have started at any one of the joints. I'm going to go ahead and come in at A and figure out what we have. You'll also notice right here that I put AB equals 0, and I put those in gray. So it's technically not in tension or compression. So at A, I have these 4 forces left. I had this 5th one here that was zeroed out. And so I have in the X direction, I have this black one to the right. I have this blue one to the left. And this other diagonal blue one is partly in the X. And then in the Y direction, I have the 400 up, and then this blue one is partly down. So we'll have to look at the component forces of that. So we'll have to use our trig in order to figure that out. So in the Y direction, we have our AY, which is this one, going up, and the Y side of AC going down. And so the Y side of AC, this is a 45-degree angle here because of our isosceles right triangle. And so ACY is going to be the hypotenuse or the magnitude AC times the sine of the angle. So we get AC sine 45. This was the value that I gave you earlier. Sine 45 is 0.707. So we'll plug that in. I'm going to refer back to this line after a little bit. It'll become handy for us. When we divide that through, we find that AC is 566. So this member is in tension because it's positive. It stays positive. It's in tension. I don't need to redraw any arrows, but I did just find my 3rd member force. It's 566. Let's see what else we can find from A, looking at it in the X direction. So in the X direction, I have AX, which is acting to the right. I have AE, which is acting to the left, and I have ACX, which is partly acting toward the left. So I need the X component of AC. So we have the 600 to the right. I don't know AE, that's actually what I'm going to be able to find. And then I have my AC cosine 45 because it's that adjacent side on this one, the X side on it. Whenever we look at this, cosine of 45 also is 0.707. And whenever I substitute in, I could actually take the 566 here and plug that in right here and figure it out. Or I could recognize that AC times 0.707, I already had listed right back up here. So I actually know that AC times 0.707 is supposed to give me 400. So that's actually the substitution that I'm going to make in here. And solving for AE, we get AE is 200. Again, it's positive. It means it's in tension. I don't need to redraw any arrows. So I just found my 3rd and 4th member forces. AC is 566. AE is 200. Those will stay blue, and we don't need to redraw them. Okay. So I have those labeled here, updated as well. So at E, so I'm just kind of working my way around here. At E, I'm going to look at the sum of the forces in the X equaling 0 and the sum of the forces in the Y equaling 0. I'm going to start off with the one at Y. At Y, I only have one force in the Y. It's this CE or EC force that I have. It's actually acting down, so I went ahead and put a negative symbol in front of it, but that's the only one I have. So my EC force, EC member force, is actually going to be 0. It's not in tension or compression. So neither of these actually are. In the X direction, I have AE, which at E, AE is going to the right. Okay, so that's actually going to be positive. Earlier we said at A, AE was pulling to the left. Okay, so I'm actually looking at this joint. AE is pointing to the right. ED is pointing to the left, and so I have AE minus ED equals 0. I already know the value of AE. We plug it in and solve for ED. And so this value of ED or DE here is 200, positive. It'll stay in tension. So when we update our picture here, CE is 0, DE is 200. And before you know it, we've actually found 1, 2, 3, 4, 5, 6 of our member forces. We only have one more left to find. So all we're looking at is CD here. And so the question is, well, do we want to look at D or do we want to look at C? And so I would just point out that I think it's easier to look at D. There's less stuff going on there. And then at D, we actually have our option. We could either look at this in the X direction at D to try to find the member CD, or we could look in the Y direction to try to find the member CD. And it technically doesn't matter which one we look at. We're going to get the same answer either way. And so in the X direction, we have DE, which is pointing to the right. It's the one that we actually just found. And I have the X side of DC. So this arrow is pointing both down and to the right. In the context of the X direction, it's going to the right. So we're going to put a positive symbol here, okay, because it's going to the right. If we were looking at the Y part of this, this CD is going down. So we would put a negative symbol in front of DCY. But we're looking at the X one. So it's a positive DCX. And so that would be DC times the cosine of 45. Again, this is an isosceles right triangle. So my angle here is 45 degrees. And so whenever we solve this, we get the 0.707. DC ends up being negative 283. Again, it comes out to be negative. So this one is actually in compression. So I'm going to redraw my arrows both at D and at C, going the other way, and change that to be 283 in compression. So both CD and BC are being compressed. AC is being stretched, it's in tension. AE is being stretched, it's in tension. DE is being stretched, it's in tension. Okay. So this is our final picture, kind of color-coded with all of our members kind of drawn in, and the way that that final picture would actually look here. All right, so hopefully you learned a lot from that and found some easier ways of having that work for you. Good luck with that.